Jet engines are marvels of engineering that power modern aviation by converting fuel into thrust. Understanding how they generate this thrust requires examining the fundamental thermodynamic cycle that drives their operation. Jet engines operate on the Brayton thermodynamic cycle, which consists of four distinct processes. This temperature entropy diagram shows how the working fluid, air, changes state as it moves through the engine. Let's examine how thrust is generated by following air through the four key stages of a jet engine. This cross-section shows the path air takes from intake to exhaust. Stage 1 is intake. Air enters the engine through the intake opening at the front. The shape of the intake is designed to efficiently capture and direct airflow into the engine's compressor section. Stage 2 is compression. The compressor section contains multiple rows of rotating blades that progressively compress the incoming air. This compression increases both the pressure and temperature of the air, preparing it for efficient combustion. Stage 3 is combustion. Fuel is injected into the combustion chamber where it mixes with the hot, compressed air. This mixture ignites continuously, creating a rapid expansion of gases that reach temperatures over 2,000 degrees Fahrenheit. Stage 4 is exhaust. The hot, expanding gases first pass through the turbine, which extracts energy to power the compressor. The gases then accelerate through the exhaust nozzle, creating high-velocity exhaust that generates thrust according to Newton's third law. Modern jet engines are axial flow engines, meaning air flows parallel to the engine's central axis during compression. This design allows for multiple compressor stages arranged in series, providing efficient compression while maintaining smooth, continuous airflow through the engine. The fundamental principle behind jet engine thrust is Newton's third law of motion. By accelerating a large mass of hot gases backward at high velocity, the engine creates an equal and opposite reaction that propels the aircraft forward. This is the essence of jet propulsion, converting thermal energy from fuel combustion into kinetic energy of the exhaust gases. A jet engine consists of several key components working in perfect harmony to generate thrust. Each component plays a crucial role in the engine's operation. This diagram shows a modern turbofan engine with its main components clearly labeled. Air flows from left to right through each section, being transformed at every stage. The intake draws air into the engine. The compressor increases air pressure and temperature. In the combustor, fuel mixes with compressed air and ignites. The turbine extracts energy from hot gases to power the compressor. Finally, the nozzle expels gases at high velocity to create thrust. The turbine is particularly important because it extracts energy from the hot, expanding gases to power the compressor, creating a self-sustaining cycle of operation. Modern commercial aviation primarily uses turbofan engines due to their superior efficiency and significantly lower noise levels compared to older turbojet designs. Turbofan engines offer multiple advantages: higher fuel efficiency through bypass air, lower noise levels, better thrust at low speeds, and reduced emissions compared to pure jet engines. Current advancements focus heavily on sustainability. The aviation industry is developing sustainable aviation fuels, or SAF, which can significantly reduce carbon emissions when used in existing engines. The CFM RISE open fan demonstrator represents a breakthrough technology aiming for a 20% reduction in fuel consumption compared to current engines, with potential service entry in the mid-2030s. The industry is exploring revolutionary alternatives like hydrogen-powered aircraft, which offer zero carbon emissions when produced using renewable energy, and hybrid electric propulsion systems for improved efficiency. Hydrogen propulsion offers zero carbon emissions and high energy density, while hybrid electric systems provide reduced fuel consumption and lower emissions, particularly suitable for short-haul flights. Digital monitoring systems represent another major advancement. These next-generation systems provide real-time performance data, enable predictive maintenance, reduce maintenance costs, and enhance overall engine operations and safety. Modern jet engine technology combines proven engineering principles with cutting-edge innovations. From advanced materials and digital monitoring to sustainable fuels and alternative propulsion systems, these developments are shaping the future of aviation toward greater efficiency, lower emissions, and enhanced performance.